let's start. So remember these questions. The first one was what the Markov chain is. So we'll start with setting up the Markov chain for RBMs. Disclaimer, for the next 3 slides, you'll not understand anything, why I'm doing what I'm doing, but it will become clear later on, okay? So let's just follow the procedure and then let's talk about why we did that procedure, okay? So we begin by defining our Markov chain. So once again, for clarity, our random variables were v1 to vm and h1 to hn, and I'm just renaming all of this as x1 up to xn plus m, okay? So at time step 0, I'll just initialize a chain with some random variable, not random variable, sorry, some random value, okay? So I'll just sample some value from the space that I have, 0, 1 raised to n plus 1, and say this is the vector which I have constructed, okay? Now I need to construct a Markov chain, so I need to tell you what x2 is going to be, what x3 is going to be, and so on, okay? In fact, I can tell you a Markov chain completely if I tell you, what 2 things if I tell you? Initial distribution and transition matrix. For initial distribution, I have just seemingly assumed a uniform distribution. I'm just saying that I'll take any possible, any value from the n plus m space. Okay, I've just taken the uniform distribution. Okay, and now I have to tell you the transition matrix, which I'll not tell you. So at time step 1, we transition to a new value of x. So this was the value of x. This was the value of x at time step 0. Now at time step 1, we transition to a new value of x, okay? So what does this mean? What do I mean by transitioning to a new value of x, and how do we do this transition, right? So let's see. So what I need to do is, given the value x equal to small x at time step 1, I need to transition to a new value x equal to y at time step 2. That's what I mean from transitioning from one value to another, right? So remember that the number of customers was transitioning from one particular vector value to another particular vector value, right? So that's how the transition happens. And the way I'm going to do this transition is the following. I'll sample a value I from 1 to n plus m, where n plus 1 is the total, n plus m is the total number of random variables that I have in my x, right? My x is a collection of random variables and there are n plus m of those. So I'll sample a value of I from this range and I'll use a uniform distribution. So a simple way of saying is I'll pick a number from 1 to n plus m, okay? Now I'll fix the value of all the variables except xi. Okay, so let's avoid confusion here. So here when I refer to xi, I don't mean the elements of the chain, I just mean the particular random variable in x, right? So I mean one of the constituents of capital X. Is that fine? Is there confusion with that? No. So what I'm going to do is, say I've sampled the value 2, I have picked up 2 as a number here. So I'm going to keep all the other random variables fixed. I'm not going to change their value, okay? And I'm going to sample a new value for this random variable using the following distribution, okay? So I'm going to sample a new value for the picked random variable using the following distribution. So this is a fair question to ask, right? I'm asking that given the values of all the other random variables, what is the probability of this random variable taking on a certain value? Is that fine? So does it make sense to sample according to this distribution? So I'm telling you how I'm going to define the transitions, right? Instead of telling you the transition matrix, right? Instead of giving you this 2 raised to n cross 2 raised to n matrix, I'm just telling you a procedure for transition, right? And of course, eventually I'll tell you how this procedure actually gives you the matrix. I want to give you the matrix, but I'm not giving it to you. I'm giving you a procedure. And now I'll show you a one-to-one correspondence between this procedure and the matrix. But right now we are just focusing on the procedure. So the procedure is very, very simple. I have some configuration of the random variable x at time step 1. I'm going to fix all the components of this random variable except one of them, right? So at time step 2, I'm going to keep all the values same except for one of these. Now, whether I should keep the same value for this variable or change it, I'll decide that based on the following probability distribution. I'm not sure whether I know this probability distribution or not. I don't know that yet, but I'm assuming that this is some probability distribution according to which I'm going to decide whether to change this value to 0 or keep it 1, because there are only 2 possible values, right? Again, this is just a procedure. Don't try to find too much meaning into it at this point, okay? Now I'm going to repeat the above process for many, many time steps. yi. Oh, okay. X of minus I is not clear. Yeah. So x of minus I means all the random variables except the ith random variable, right? So this is xi given x1, x2, x3 and not xi and all the other guys. Okay? And x minus I, this small guy, is a vector of dimension the small xi is a vector of dimension everyone n plus m minus 1, because I have dropped one random variable from there. Is that fine? Nitesh, you seem to have blanked out. Is that fine? Okay. So n plus m minus 1. Okay, is that clear now? Okay, so the notation I should have clarified. Now repeat the above process for many time steps. So what does it mean to repeat the above process? Again, now I am at time step 1. Again, I am going to pick up one of these random variables. Say I picked up the random variable 3. I am going to set the value of all the other random variables as it is. I am not going to change that. And for this random variable, I am going to decide whether to change its value or not given the rest of the configuration. Is that fine? And I just keep repeating this. And notice that it's not necessary that the value will always toggle. It can actually remain the same also. Oh no, not here. Yeah, it can actually remain the same also. Right? So at this time step, again I picked 1 as the random variable which I'm going to sample again and fix all the remaining variables. And at this time step, based on this distribution, I actually ended up keeping the same value. So now we have to live with this for the next 15 slides or so. Okay. So yeah, the last column is constant, right? Because we have not picked any of those random variables. We're just working with these. So for the next infinite slides, just assume that the last column is all ones. Okay, thanks. Clear, right? You seem to be. Oh, we changed it at some time. No. We never picked this guy, right? Unless we pick that guy, it's not going to change. So we picked this guy. Is that clear? We're picking one variable, either changing it or keeping it the same based on this distribution. Is that fine? We'll come to that. Whether we are given this distribution or not, we'll come to that. Okay? So that means you're asking the question that is this computable or not, right? And computable efficiently or not, right? If so, then only I can transition. Okay, fine. So again, I've just given you the procedure. I need to explain the procedure yet. Is that clear? This is how my Markov chain is set up. Okay, so what are we doing here? How is all this related to our goals? Nothing is clear at this point, right? So, but we'll try to make it all clear. Now, we are violating the basic principle. To define a Markov chain, I need to give you the transition matrix. And I'm just shying away from that. I'm not giving you the transition matrix because I cannot give you one. Because I cannot give you 2 raised to n plus m cross 2 raised to n plus m values, right? Not in the duration of this course for sure. So that's why I'm not giving the transition matrix, but we'll have to get to the transition matrix actually. How is it easy to create this chain? And that's the question which he was asking, right? At every transition point, I need to compute some probability. I need to compute that probability. I have not even told you what that probability is. So I need to tell you that this transitioning is easy. I have not done that. And of course, I have not even shown you that the stationary distribution of this Markov chain is the distribution that we care about, right? I have not even told you what the transition matrix is, then the question of the stationary distribution does not even arise, right? So these are 3 questions that I need to answer. I need to tell you what is the transition matrix explicitly in this procedure. I need to show that it's easy to transition. That means it's easy to draw these samples x0, x1, x2 across these time steps. And finally, I need to show you that this indeed has the stationary distribution as a distribution that we care about, which is the joint distribution of our random variables, right? Where x is equal to a collection of the visible as well as the hidden variables, right? So you agree if I answer these 3 questions, then you will not give me these blank faces that you're giving me right now? Can we have a deal? Yes or no? Everyone? Okay, not everyone yet, but okay. So let us answer these questions one by one, right? So first, let us talk about the transition matrix. We have actually defined a T. When I was giving you this procedure, I've actually defined T, although I did not tell it to you explicitly. And now let me tell you what this T is. What would T actually contain? What would it actually contain? Probability of transitioning from state A to state B for all possible A and B, right? That's what it will contain, right? From any state X to any state Y in my sample space, and my sample space is 2 raised to n plus m. Okay, At least we know what T contains. So T is this kind of a matrix. When did we define such a matrix? Did we define such a matrix? Did we define such a matrix? Actually we did. We defined a very simple matrix T, and it allows only certain types of transitions, right? So let's see what it means, right? In particular, under this matrix T, we allow only those state transitions which differ from each other at maxed in one random variable. So that's the same as saying T of xy is equal to 0 if, do you get the question? So we define the procedure in such a way that we allow only certain types of transitions. That's the same as saying that I will not allow you to transition from state x to state y if they differ in more than one random variable. That means T of xy is equal to 0 if x and y differ in their values for more than one random variable. Is it clear? So you see I have defined a very, very sparse transition matrix, and that's why I don't need to give you it explicitly. I don't need to give you the 2 raised to n plus m cross n plus m values. I have told you what are the zeros in this, so I just need to focus on the non-zeros. And what were the non-zeros? Did I give you a formula for the non-zeros? Did I? Okay, so let's see. So we define T using this. I urge you to read it, understand it, and explain it to me. Focus on the zero otherwise, that's always easy. So let's see. Okay, so let's see, this is our capital X. I think there's some problem here, but let's not tell them. So x1, x2, x3 up to xn plus m, right? So it's saying that P of xy is equal to 0, and I told you when it is going to be 0, right? So the otherwise case is clear. For the first condition, this is just a more formal way of saying that there exists an I, there exists a number I belonging to 1 to n plus 1 m, such that for all the random variables belonging to x, if the index of that random variable is not equal to I, then the value is the same across these two states. Do you get that? How many of you are able to read this now? So I have these two states, right? I have the state x and I have the state y. What this cryptic looking first condition is telling me, right? If there exists a value I such that for all the things which are not equal to I, those state values are the same for x and y. So x and y, remember, are n plus m dimensional vectors. So what it is telling is n plus m minus 1 values are same, and one of these values may or may not differ. Okay? If that is the case, if that is how x and y look, then the probability of transitioning from x to y is given by this. So now let's break. Is that clear? If the if condition, okay, everyone gets the if condition, please raise your hands if you don't. So you have a state x and state y, okay, and so what the first condition is telling you is that if there is one random variable, one index for which apart from that index all the other state values are the same, okay. Now why this particular form? What is this? So what was qi? Qi was the probability of picking that value I, right? So that has to be, so I have picked the value I, and then what does this mean? Actually what is this actually a shorthand for? Can you write the full formula for this? What is this a shorthand for? Are these random variables? These are values, assignments. So what is the full way of writing this? X equal to yi given, or rather xi, right? One of these guys taking on the value yi, given that all the remaining guys have a certain value. So this is n plus m minus 1, and this is of course 1. Do you get that? So is it clear now how I had defined the transition matrix? How many of you get it that the procedure explicitly defined a transition matrix, or rather implicitly defined a transition matrix? Please raise your hands. Okay, fine, good. So Qi was a probability of picking I as that random variable which is going to differ and all of the others are not going to differ. And Pxi equal to yi given the remaining random variables essentially tells us what is the probability that the ith random variable will take on a certain value given the values of all the other random variables. Is this easy to compute? What are our x's? Just a minute. What are our x's? X is actually equal to everyone. It's a collection of v comma h. This is some conditional distribution defined on v comma h. Do you get that? Do you think it would be easy to compute that? Not sure, so we'll get to that, okay? But at least are these definitions clear to you, what each of these quantities that you see mean? This if condition is clear to everyone? Please raise your hands. If you don't understand that, you'll not understand anything for the rest of the course. No, how many of you don't understand? Please don't raise so many hands. I mean, you do if you don't understand, but how many of you don't understand? Except you don't understand. What were you waiting for? Okay, what do you not understand? No, that guy. We have bigger problems actually. Okay. Huh? Both the circles you don't understand. Okay, fine. So what I was interested in is P of xy, right? Okay, and it would have been better if I had called this T of xy. So I'm interested in the probability of transitioning from a state x to a state y. Okay, so let's have this as x. And this vector of course has the assignments for all the random variables that I care about up to n plus m. That's some assignments, right? So these are zeros, ones, 0, something. Now I'm interested in transitioning to a new state y. Okay. Now what the else part, that means 0 otherwise, tells me is that if x and y are going to differ in more than one random variable. So if I have y such that it's, I actually tried to erase it with my finger. Okay, if I have a y which looks like this, right? So it's different from x in two values. Such transitions I was not allowing. If you remember the procedure, I was only allowing you to change one value. That's the same as saying that if x and y differ in more than one value, then the transition probability is 0. Is that clear? So that's what the else part says. And if you understand the else part, then the if part is just the counter of that, right? So what the if part is saying, this cryptic looking formula is saying is that there exists an I belonging to n plus m, right? 1 to n plus 1. You have sampled one I such that except for this I, the one which I have circled, for any other v, any other index which is not equal to I, x of v is equal to y of v. Right? So these are all the indices, the ones which I am now highlighting with an arrow are all the indices which are not equal to I. For all those indices, x of j, let me call them j, is equal to y of j. Is that clear? That's the same as saying that these two states do not differ in these values, in this n plus m minus 1 values. They are only allowed to differ in this one value. Now for this one value, whether to keep it same or different, that's defined by this probability distribution. Okay? So first thing that I need to think about is sample a value of I. That's Qi. Once I have done that, and now tell me what's the probability of transitioning to a new value given all the other random variables have been fixed. So that's what this condition tells me, right? And what I was telling you is that that's actually a short form right? Is that clear? Xi, okay? Where x minus I is all the other random variables in your collection. How many random variables do we have? N plus m, right? So this condition is on n plus m minus 1 values, and what you have here is one random variable. Okay? Fine? Okay, fine. So is that clear to you at this point? Okay? Now Qi, my claim is it's straightforward because we assume it's a uniform distribution. So drawing a sample from this distribution is not hard. What I need to show you that this other quantity is also easy to compute, okay? And we'll get there. That's what I'm going to show you now. So, yeah, this is messed up. Just focus on the explanation that I gave. Okay? I did not see it properly. I should have done that. Okay? Just focus on the explanation which I gave you. If that is fine, then I'll just change this condition to match that. Okay? Yeah, but all right from starting the description of RBMs, I had said that we are only going to focus on binary variables. We will not be covering that in this course. Okay, we'll have to assume certain forms for this distribution and so on, right? But right now we are not interested. Okay, but I've still not shown you that this is easy, by the way, right? I need to show you that. P of x to x. Yeah, that's the same formula, right? So in that case, yi is equal to xi, right? Yeah. Okay, let's not confuse the others. Okay. Fine. Yeah, I get your point. So I think there should be a summation, but I'll just get back to you. Okay. Anyone else? Okay. Is it clear? Despite messing up the most crucial side of the lecture, is it clear? Okay. So what I have done now, I have given you I've answered the first question. What is the transition? Is there some confusion here? First bench? Sure? Okay. So I've answered the first question, what is the transition matrix? And the answer is, it's a very, very sparse matrix. So I don't need to define 2 raised to n plus m cross 2 raised to n plus m values. I need to define only a few of those, and I've given you the form for that. Is that clear? Okay. Now we look at the second question, which was, how is it easy to create this chain? That means at every point, what's the computation that I need to do? I need to fix one variable, that's easy. Once I fix this variable, I need to compute that probability value. Okay. So what's the probability value that I need to compute? This one. That the ith variable takes on the value yi, right? Given all the other random variables. But this is how you would compute it, right? This is how you would compute it, because all you have is the joint distribution, right? We are always learning the joint distribution. So you have p of x. So that's what you have. How many parameters does p of x have? How many parameters does p of x have? How many random variables does x have? How many? N plus? Each of them is binary. So how many parameters does this have? 2 raised to n plus m. That means we have completely forgotten the lecture on RBMs, but it's okay. So 2 raised to n plus m. Okay, so this is not easy, right? This is, again, the quantity on LHS requires you to give me 2 raised to n plus m values. So how is it easy? What do we do to make a joint distribution easy? Factorize it. Did we factorize it? Did we factorize it for RBMs? Yes? Okay, if you have forgotten it, let's see. Okay, this is not actually hard, and I'll tell you why this is not hard. So consider the case when I is less than equal to n. That means the random variable that you have picked to change is one of the visible random variables, right? You have n plus m values. The first n are the visible variables. Again, goofed up. Okay, n and m we have confused throughout, right? So it's one of the visible variables. Okay, let's just focus on that. Okay, so if I is less than equal to m, that means I have decided to change one of the visible random variables. So if I have done that, then this is the probability that I'm interested in, which is the same as saying I'm interested in the following probability distribution, right? That what is the probability that the ith visible variable takes on a certain value given the remaining visible variables and the remaining hidden variables, okay? But this actually simplifies because of the independence assumption. And I just need to compute this probability of the ith visible variable taking on a certain value given all the hidden random variables, and that is equal to some z. Again, is it easy to compute this z? Did you derive this in your assignment? Did we derive this in the last class? What was this? Why are RBMs neural networks? What is this quantity? Sigmoid of gradient. Who said gradient? Random. Sigmoid of summation wij vj plus ci. I mean, if you don't remember, you remember that there was a neat closed form solution to this. Is it hard to compute this? No, right? It's just a simple vector multiplication. right? It's just a sum of wij, wij plus ci. So that means I can compute the probability of the visible variable taking on the value 0 or the value 1. Okay, because those are the only two values possible, and I can compute this very easily. So this was the term that I was worried about, and I was worried about whether I can compute this efficiently. On the previous slide, I scared you by saying, oh, this has 2 raised to n plus m parameters. But on this slide, I'm making a case that we have already simplified this in the previous lecture, where we had said that this just boils down to computing a sigmoid function. So I have this sigmoid function, and I will set the value to 1 with the probability z, and the value to 0 with the probability 1 minus z. How do I do this in practice? How do I do this in practice? So I computed the sigmoid. Suppose it gave me the value 0.2. Okay, that means z was 0.2. That means I need to set this to 0.2 with a probability 1 and 0 with a probability 0.8. How will I do this? Everyone? You will pick up a random variable, a random value between 0 to 1 sampled from a uniform distribution. If the value is less than 0.2, you will set it to 1. If the value is greater than 0.2, you will set it to 0, right? So this is straightforward. There is no problem in doing this, okay? So essentially at every time step is the same as saying that we sample a I from a uniform distribution Qi, which is very easy to do. Once we have done that, we sample from the Bernoulli distribution with mean z. Right? That's exactly what we're doing. It's a Bernoulli distribution because it have binary variables which can take on only values 0 to 1. The mean of the distribution is z. That means the probability of heads or the probability of taking on the value 1 is z. So you just need to draw from this distribution. And I told you the exact procedure of how you will draw from this distribution. You will actually sample a number from a uniform distribution between 0 to 1. If the value is less than z, you will set it to 1. If the value is greater than z, you will set it to 0. Everyone is clear? Everyone sees that this is actually easy to do. So what is the question that I've answered now? It is easy to draw samples from this chain starting from any value x0. I have x0, I know how to transfer to x1, x2 and so on efficiently. Right? The computations involved are very simple. Is that clear? So now we have answered the first two questions, and now what was the third question that we need to answer? That the stationary distribution is P of x, right? We need to show that the stationary distribution of this particular Markov chain with the transition probabilities defined by that T, which I just very clearly explained to you, is going to be P of x. That's what I need to show, okay? How many of you are completely lost at this point? How many of you are following everything at this point? Oh God. Okay, the safe question is 80%. How many of you are following 80% at this point? Please raise your hands high up. Okay, that's good. 20% of course you'll go back and read the slides. That's why the slides are there. So to prove this, we are going to rely on the following theorem, which is something known as the detailed balance condition. What this says is that if I want to show that a certain distribution pi is a stationary distribution for a Markov chain with transition probabilities P of xy, right? So just be aware that I'm calling T of xy as P of xy, right? With these transition probabilities, and we actually had defined P of xy on that slide which shall not be named. It is sufficient to show that for all xy belonging to my sample space, the following condition holds. Okay? I know it's very hard to understand what this condition is, why we need to prove it and so on. So I'm not going to prove this theorem. We are going to take this theorem for granted that the detailed balance condition is sufficient to show that the distribution pi is a stationary distribution for the given Markov chain, right? They are going to have faith in this theorem, and we'll show that for our particular case, this condition holds. Hence, the distribution that we care about is the stationary distribution. So you see where we are headed now. So we're going to rely on this theorem and prove what we need to prove. Okay. So now, what are P of x comma y and what is pi? These are the two things that we'll first define clearly, right? Because these are the two things that we need here. So first, P of xy. Okay, that's what this is. I allow only transitions of one particular random variable, and for that random variable I define it, I was calling it P instead of pi, but now on I'm going to change this. So we are going to refer to P of x, which is actually P of v comma h, as pi of x, right? Just to be consistent with the notation. Okay? Everyone fine with that? Just P has become pi. Okay? And for shorthand, instead of saying probability of capital X taking on the value small x, I'll just call it as pi of x. So when I say pi of a small letter, it means that the capital letter taking on the small letter value, whatever that means. Okay. Okay? Capital X taking on the value small x. Is that fine? I'm just going to refer to that as shorthand. And similarly, when I say xy, it actually means transitioning from right, that's what it means. Is that okay? Right? So you know what pi is and you know what p is, and now we need to prove that this detailed balance condition holds. Okay. Now there are three possible cases. First, let's agree that these are the three cases that cover all possible cases. The first case is when x and y actually differ in more than two values. Okay, that's one case. The second case is when x and y do not differ in any value. Okay, that means they are exactly equal. And the third case is when x and y differ only in one value. Are there any more cases possible? No, it could be visible or hidden. So the same argument which I gave for visible, that if it was less than n, then it's easy to compute. The same argument holds for if it was between n plus m. So I'm saying there are three possible cases. One is when x and y differ in zero values. That means they're exactly the same. The other case is when they differ in exactly one value. And the third case is when they differ in more than one values. Right? This covers everything. There's no other case possible here. Is that clear? Okay. So if I prove that for all these three cases the detailed balance condition holds, then I'm done. Is that okay? So let's start with the easy case one, which is x and y differ in more than one state. Is that clear? More than one random variable, sorry. So in this case, by definition, you want to prove that pi x pxy is equal to pi x into 0, which is 0, and the other way around also it's 0. So trivially the detailed balance condition holds. The case 1 was very easy, right? The greater than 1 case was very easy. When the states x and y differ in more than one random variable, it's trivial. Let's look at the other case. When x is equal to y, that means the case when they differ in 0 random variables. In this case, again it holds trivially. Pi x into pxy is the same as pi x into pxx, and pi y into pyx is again the same as pi x into pxx, right? So again, trivially the detailed balance condition holds. So far clear? Okay. Now we come to the case where x and y differ in exactly one random variable. Okay. So in that case, by definition, this is our LHS, right? So we want to show that this LHS is actually equal to the following RHS. This is what we need to show. Okay. So now by definition, the second quantity P of xy is actually equal to this. Everyone fine with this? Do you guys want a break? It's the only time I get an answer immediately. It's already 6:30. We have a long night ahead of us. There are 39 out of 61, right? So, okay, let me just finish this part so it's logically done, and then we'll take a break. Okay. So I've just substituted the value of pxy, which was defined on the previous slides. Is that okay? Fine. Now I'm just going to do some very simple trickery. So let's again be sure that this is the value that one of the random variables takes on, that is the ith random variable takes on, and this is a vector because this is the value that the remaining random variables take on. Okay? Is that fine? Now this thing, I can write it as this thing. A conditional distribution is joint over marginal. How many of you get this? Please raise your hands up and high. Okay. And this guy, I'm just going to split it into xi and x minus 1. Right? Is that okay? So this is the same as saying that xi is equal to small xi and the remaining random variable is equal to x minus I. Is that okay? Right, I've just split it into two parts. I'm just rearranging the terms. So I've taken this and put it here, and I've taken this and put it here, and I've attached this qi here. Just a rearrangement of the terms. Okay. Now, what is this quantity? This is xi given x minus I. And what is this actually? Pi y, pi x, pi z, pi. What is that, this quantity? Everyone? Anyone who has a doubt about it? Please raise your hands, otherwise you will not understand anything in the rest of the course. Okay, so this is pi y and this is xi given xi minus 1. Now what is this combined? Actually there is one more step here. This x minus I can just call it even y minus I, right? Because for the minus I variables, x and y are same. Okay, so now what's this circled quantity? P of yx. Okay, so starting from the LHS, we have come to the RHS. So we have shown that the detailed balance condition holds for all the three cases which were possible. Hence, pi is the stationary distribution of Earth, Jupiter, Mars, what? The stationary distribution of this Markov chain, right? So we have set up the Markov chain in such a way that we have been able to prove that the detailed balance condition holds for all these three cases. This is the case 1, this is the case 0, and this is the case greater than 1, right? For all these cases it holds. So that means if we run this Markov chain for enough number of time steps, we are going to reach the stationary distribution that we care about. If we keep sampling values from this Markov chain, eventually we will get values which are same as if they had come from the distribution that we care about, right? And even after we reach the stationary distribution, the sampling process remains the same, right? You are going to use the same sampling process which was set one value, keep everything as the same and just change this value. But now with this simple procedure, actually you have started getting samples which come from your joint distribution that you care about. So you see the overall trick, right? You can set up a chain which is, okay. So these were the things that we cared about, right? Define what our Markov chain is. Have we done that? Right? Have we defined the transition matrix? Done. Okay. Is it easy to sample from this chain? Done. Have we shown that the stationary distribution of this chain is the distribution that we care about? Done. Have we shown that the chain is irreducible and aperiodic? Done. We kind of showed everything that we had to prove. To what effect we are proving all this is still not clear, but we'll get there. But there's one thing which we have not shown. Remember the statement of the theorem had that this chain has to be aperiodic and irreducible. I have not proved that. I have not even defined what aperiodic is and what irreducible is. So we'll quickly take a look at it. It's the easy part of this lecture, so we'll just do that quickly. So first I'll look at the definition of irreducible. So a Markov chain is irreducible if one can get from any state in omega, right? So omega is your entire state space. This was earlier defined using that stylish x, or it's 0 to 1 raised to n plus m in our case. So in your state space, if it is possible to reach any state starting at any initial state, right? So you have 2 raised to n plus m possibilities for this, and you have 2 raised to n plus m possibilities for this. What I'm saying is that if I want to reach from any state to any other state, then there exists a value k such that after that many steps, there will be some probability that I'm going to be able to reach this other state, right? So in other words, the other way of looking at it is that it is not the case that if you have one of these 2 raised to n plus m values that you start from, the remaining 2 raised to n plus m minus 1 values are reachable from here. It's not that there is a particular state which is not reachable from there. So it's not the case that the probability of reaching a particular state starting from any other state is 0. Right? That's what it means irreducible, because the chain will continue. Is that fine? Is the definition clear what irreducible means? Please raise your hands if it's clear. So it basically just means that I know that after some case steps at least, there is a finite probability of reaching any state starting from any other state, right? So this holds for all I comma j belonging to omega. So what about our Markov chain? Is it irreducible? So a Markov chain is irreducible. So you have these 2 raised to n plus m values that your states can take, right? So let's say I started with one of these values, okay? And now the question that I'm interested in is that I'm going to run this Markov chain for many time steps, okay? Now the question that I'm asking is that, is it possible that if I take any other state from this 2 raised to n plus m states, can I reach that state even if I run it, and I'm not putting any restriction on k, right? I'll keep running it, okay? Is it possible that at some time step k, arbitrary time steps k, all these 2 raised to n plus m values are reachable irrespective of where I start from, right? So if there is a break in between, right? If there is a case that I cannot reach one of these values, then it would mean that this probability is equal to 0 for all k's. There does not exist a single k for which this probability is greater than 0. That means no matter how long you run the chain, starting from a particular state, you cannot reach this other state. If that happens, the chain, if that does not happen, then the chain is called irreducible. That means given any state, starting state, you can reach all the other states after some number of time steps. And that's what irreducible means. So the Markov chain that we had, is it irreducible? Yes, right? And you can take the very simple case. The most difficult transition would be starting from all zeros and going to all ones, right? Because you're allowed to only change one value at a time, right? Even in this case, it's possible to reach from all zeros to all ones. And if you could do that, then it's possible to reach any state from anywhere. Right? This is a very intuitive explanation. Is that clear? Everyone gets this? It should be straightforward to see that the chain is irreducible. Okay? So we can prove this more formally, but we are not going to do this. We'll just live with the intuition that this chain is irreducible. Hence, one red mark which we had in our theorem, that it was true only for irreducible Markov chains. We don't need to worry about this. Now, the other thing is even more cryptically defined. So a chain is called aperiodic if the greatest common divisor of this set is 1. What is this set? What does this set contain? All the time steps at which, starting from the state I at time step 0, I will end up in state I again, right? Starting from state I at time step 0, there is a finite probability greater than 0 that I will end up at time step at the state I again at the time step k. So this is actually a set of the following form, that maybe if I start with some value or some I at time step 0, at time step 1 it's possible that I'll stay in the same value, at 2 it is possible, and so on. This is just a collection of those numbers. Okay, so this set is a collection of all the time steps at which, starting from one value, there is a finite chance that I can reach that value again. Okay. Now, instead of aperiodic, let's talk about periodic. If this was periodic, what would you expect this set to contain? What does periodic mean? Something which happens periodically. Something which happens periodically, right? So then what kind of values would this set contain? What kind of values would this set contain? Multiples of some number, right? So it contains, so this is all fine. If it contains these kind of values, right, 3, 6, 9, 12, that means it's saying that starting from state, from a value of, from a state I at time step 0, I can only reach the state I again at these multiples. That means this is periodic, right? I cannot reach it at anything which is not a multiple of this period. Is that fine? So that's what periodic means. So periodic means that this set would have a greatest common divisor which is greater than 1, right? Because the greatest common divisor would actually be the dash of the Markov chain, the period of the Markov chain, right? Now what aperiodic means is that I will get a set which does not contain such multiples, it contains some arbitrary values. So it might contain 1, 3, 5 and so on. So now if I try to take the greatest common divisor of this set, I'll get 1. 1 can be the only greatest common divisor of this set. So it just means that there is no pattern to this, there is no period after which this repeats. It can arbitrarily return to the same state after any number of time steps. Is that clear? So it always helps to understand periodic, then aperiodic is just the reverse of that. So this is what periodic is. So aperiodic, and if it's periodic, you will have a greatest common divisor which is not equal to 1. You will have the greatest common divisor as the period of the chain. But if it's not periodic, then you'll just have the greatest common divisor as 1, because that's only the greatest common divisor of all the elements in your set. No, strictly speaking, no, right? So periodic has to be 0, 2, 4, 6, 8 and so on. So you're just changing, yeah? So by shifting then it would be periodic, right? So then in that case it would be periodic. K is a natural number. I had asked for a different n, but okay. K is a natural number, right? Because it can be time steps which are greater than 1. Okay? Right? So, I mean, just don't look at, this is unfortunately the way of stating what aperiodic is, but don't focus on that. Just understand what periodic is, and aperiodic is just the opposite of that. Is that clear? Okay, and that's why that greatest common divisor comes in there. Now, intuitively, do you think our chain is periodic or aperiodic? Aperiodic, right? So again, we can formally prove this, but we're just going to rely on the intuition that this is aperiodic and move ahead. So now I'm done with all the parts of the proof. So I have set up a Markov chain which is easy to draw from, and I've shown that the stationary distribution of this Markov chain is the distribution that we care about. Even when I reach the stationary distribution, I can still keep following my process of sampling, which is the Markov chain process. But now after this point, I'll start getting samples as if they were drawn from P of x or pi of x. Is that clear? Fine. So I have done what was required.